on this graph, this is straight from your caboodle textbook. Here's a diagram showing some ionisation energies as you go across a period from left to right. And it asks you here to draw a cross on the diagram to show the first ionisation enthalpy of aluminium. Well, remember, the first rule is write out the electronic configurations before deciding on your value of your ionisation energy. So if you write the electron configuration of the element before, magnesium, you can see that the next electron, the highest energy electron for aluminium, has gone into a 3p subshell, which is of higher energy and also shielded by these electrons. So it therefore follows that aluminium doesn't follow the trend, and therefore the ionisation energy, the first ionisation energy, is going to be lower than that of magnesium. So next you're asked to write an equation showing the first ionisation energy of aluminium, and it's really important here that you put the state symbol in. So that's 1 mole of gaseous aluminium atoms losing electrons to become 1 mole of positively charged aluminium ions, and you write the electron on this side with its negative charge. This now leaves us with an ion with the electron configuration 1s2, 2s2, 2p6, 3s2. So the next question asks us which ion has got the electron configuration 3s1. So that would be when an Al plus ion loses yet another electron to form Al2 plus, and there's its electron. So it would lose a 3s electron to become 3s1. So the new ion is Al2 plus. This equation here shows the second ionisation energy for aluminium. Here is the second anomaly in the trend. So the trend, remember, as you go across a period, is a general increase in ionisation energies with 2 anomalies, 2 elements that deviate from the trend. First is aluminium, and now let's look at sulfur. If you write out the electron configuration of these 2 elements, there's phosphorus and there's sulfur, the shielding is the same and the electrons are going into the same energy level, so the same distance from the nucleus, but the 4th electron, the 4th 3p electron, is forced to pair up in sulfur, and that causes therefore some repulsion between those electrons, and therefore less energy is required to remove that electron. Now this graph here is looking at second ionisation energies, and again you can see the general trend is there is an increase in energy needed to remove electrons, but again we have some anomalies. Now this time, if we look at the second ionisation energy of sulfur, and that is when sulfur plus ions become sulfur 2 plus ions, write the electron arrangements underneath. So sulfur plus ions have a 3p3 arrangement, and therefore when they become S2 plus ions, an electron is lost from the 3p subshell. Now if we look at the element before, which is phosphorus, the electron for the phosphorus is coming from so P plus ions are 3p2 and they become 3p1. So with both, electrons are being lost from exactly the same subshell, from exactly the same sub-energy level. So now we go to look at the nuclear charge. Phosphorus has got 15 protons in its nucleus holding onto these electrons, but sulfur has got 16 protons. And therefore, in this case, sulfur has a greater nuclear charge. So if we're now to look at this trend again, there's silicon, there's phosphorus, and sulfur therefore is going to have an even higher ionisation energy because the nuclear charge of the S plus ion is greater than the P plus ion. So the aluminium 2 plus ion has lost 2 electrons, so those electrons will have gone from the 3p, where there was 1 electron, and it will also have lost an electron from the 3s. So this is the electron configuration of the Al2 plus ion. So now it says write an equation to show the process that occurs when the second ionisation energy of aluminium is measured. So remember, the second ionization energy is when a mole of positively charged ions in the gaseous state loses electrons to become 1 mole of 2+ ions in the gaseous state. So the next question is, why is the second ionization energy of silicon lower than the second ionization energy of aluminium? And again, we use our usual rule, which is write out the electron arrangements. So let's question ourselves why the second ionization energy of silicon is lower than the second ionization energy of aluminium. Again, write out your electron arrangements, and you can see here that the outer electron in silicon is in a 3 subshell, which is of a higher energy and more shielded. So therefore it's easier to lose this 3p electron, and therefore its ionization energy is lower. For aluminium to lose an outer electron, it would need to lose an electron from a 3s subshell, which is lower in energy, less shielded, and therefore it's more tightly held. And this shows the importance of writing out your electron arrangement when explaining ionization energies. The next question says, predict the element in period 3 that has the highest second ionization energy and give a reason for your answer. So if you were to write out electron configurations for all of the elements in period 3, if you now write out the electron configurations for all of those elements, and you go down, going across from sodium, magnesium, aluminium, so these are the positive ions, you'll see that in fact sodium, to lose an electron, we would now have to take the electron from the second energy level, because sodium's electron configuration is now 1s2, 2s2, 2p6, and therefore its electrons are closest to the nucleus, and we have to take electrons from a lower energy level. So the answer to that is, in this exam question, you've been asked, given the successive ionization energies of an element, which element that is. So let's look at the data. They've told us that it's in period 3. And therefore, if it's in period 3, you need to get your periodic table in order to identify that element. So what we then do is we look at the successive ionization energies, and I always cover the last 2 digits to simplify it. So it goes from 7 to 15 to 32 to 43, and then there's a massive leap from 43 to 161. And this big jump in ionization energies between the 4th and the 5th energy level suggests that these electrons in the 5th and 6th are much closer to the nucleus. So if we were to draw a GCSE diagram, it suggests that the first 4 electrons are in the same energy level, and therefore there's not much difference between them. And remember, as you take off an electron, the other electrons tend to move closer to the nucleus, and therefore they become harder to remove as there is more attraction. However, when we've taken off these 4 electrons and we now get to the 2 electrons that are right next to the nucleus, the energy required to remove these is even much higher because they're closer to the nucleus, and these electrons here are shielded by these inner electrons. These inner electrons here are not shielded. So what we do is we count the ionization energies that are close together, so that's 1st, 2nd, 3rd, 4th, and that suggests therefore that this element is in group 4, because then there's a massive jump between the 4th and the 5th ionization energies, and therefore that suggests that the 5th electron is in an energy level closer to the nucleus. The next question asks us why the ionization energy of every element is endothermic. So remember, endothermic means heat requiring. Heat energy needs to be put in to the chemical reaction. Now in this case it's not a chemical reaction. What we're doing is breaking the electrostatic attraction between that positive nucleus and the outermost electron. So there's attraction there which we call electrostatic attraction between that negative electron and that positive nucleus. So the way we would explain why it's endothermic is that energy is required to overcome the electrostatic force of attraction between the positive nucleus and the negative electron. So the elements in periodic 2, like period 3 and period 4 and 5, show periodic trends. That's repeating patterns. So we know as we go across the period, because the proton number is increasing, that the energy required to take off that electron increases because of increasing electrostatic attraction. Now also, because of that electrostatic attraction, let's have a look at a lithium atom, a simplified model of a lithium atom. So lithium, we know, has got 3 protons, 3 positive charges in its nucleus, and its outer electron exists in an s subshell. Now let's think about what happens as we go across that period. Well, as we go across the period, the number of protons is increasing. And as the number of protons increases, remember the nucleus is just a tiny point charge, and therefore we don't take into account the actual size of the nucleus because it's negligible. But as we go across a period, that nucleus is becoming more attractive. And the effect is to cause the radius of the atom to shrink. So when we get from lithium all the way across to neon, neon is going to have the smallest atomic radius because it's got the highest nuclear charge. Compared to lithium, which has got 3 protons in its nucleus, neon has got 10 protons in its nucleus. So the trend in atomic radius is for the radius to shrink, to get smaller. So in answering the question, which one has the largest atomic radius, the answer is carbon. And the reason why carbon has the largest atomic radius, carbon has 6 protons in its nucleus, whilst fluorine has 9 protons in its nucleus. So your answer would be that the fluorine's nucleus is more attractive to the outermost electrons, and therefore the size of the atom is reduced. So when we're talking about the radius, that's from the nucleus to the outermost electron. So the atomic radius of fluorine is much smaller. So the trend as you go across the periodic table is atomic radius decreases because the nuclear charge increases. The next question is, state the general trend in first ionization energies from carbon to neon and deduce the element that deviates from this trend and explain why this element deviates from this trend. Whenever you're asked to describe or explain ionization energies, the first rule is you must write out the electron configurations. So the electron arrangement for carbon is 1s2, 2s2, 2p2. So here we'll put the electrons in boxes which represent the orbitals. There's the outer electron arrangement of carbon. Here is the outer electron arrangement of nitrogen. So carbon has got 6 protons in its nucleus. Its electrons, its highest energy electrons, have just gone into the 2p subshell. Nitrogen's highest electrons have gone into a 2p subshell as well, all occupying the orbitals singly because they're all of equal energy. When we get to oxygen, there are 4 p electrons, and therefore a 4th electron is forced to pair up in one of the 2p orbitals. So in fluorine we have 5 p electrons, and now we have 2 of the p orbitals filled, and finally there's this half-filled p orbital. Then when we get to the next element, neon, with 10 protons, the p subshell is now completely filled with a pair of electrons in each p orbital. So let's now look at the trend in ionization energies. Well, obviously, as we're going across this period here, the number of protons is increasing. So the nucleus is getting increasingly more attractive. And therefore, if we go from the elements from carbon, nitrogen, oxygen, fluorine and neon, we're going to get a general increase in the ionization energies because of an increase in nuclear charge. However, the word here said which element deviates from this trend, this general increase. And we know the one that will deviate is oxygen. And the reason why oxygen deviates is electrons are now starting to pair up, and therefore there's some repulsion. So the general trend is carbon, nitrogen, but then we have a dip at oxygen because of this pairing up of electrons and repulsion. And then the trend carries on. So the element that deviates is oxygen. If we repeated the trend going across period 3, we would find that sulfur would deviate because sulfur's electrons will be going into a 3p, would be pairing up in the 3p subshell. So remember, all of the elements in this group have got 4 electrons in their p subshell. To answer this question, therefore, you must say nuclear charge increases as the period is crossed from left to right, and therefore the ionisation energy increases. The element that deviates from the trend is oxygen, because the electrons are now starting to pair up in the 2p subshell, or there is repulsion between electrons in the 2p subshell. And remember to name the subshell. Don't use the word it. So now we're going to look at this question here. C, an equation including state symbols for the reaction that occurs when the first ionisation energy of carbon is measured. So that's quite simple, because that's 1 mole of carbon atoms in the gaseous state losing electrons to form 1 mole of positively charged carbon atoms. It's really important you put the state symbol. So the next question said, explain why the second ionisation energy of carbon is higher than the first ionisation energy. And again, write the electron configuration out. So carbon's electron configuration is 1s2, 2s2, 2p2. And again, we're going to put the 2p electrons into orbitals. Carbon plus will have lost one of its highest energy electrons, and therefore that electron will have come from a 2p, because they're the highest energy electrons. So carbon plus has this electron configuration. Now both electrons are coming from the same energy. However, as an electron is lost, so there is our 2p subshell with electrons spinning in opposite directions. There's our carbon nucleus. When an electron is removed, the electron can now get closer to the nucleus because there's this overall positive charge and the attraction to the nucleus increases. Let's say that again. The increased positive charge on the carbon ion, attracting only 1 electron, causes the radius to decrease, and therefore the attraction increases, and therefore the second ionisation energy is always higher. Now the next question says, deduce the element in period 2 from lithium to neon that has the highest second ionisation energy. So here's the period going from lithium to neon. So of course you've got to look at your periodic table. The proton number is increasing, but this time we're looking at second ionisation energies. So we're going to write out the ionisation energy, the electron arrangement for each of these positive ions as we go across. So each of these is the ion, the electron arrangement of the ion, and not the atom, to get the second ionisation energy. So first of all, lithium was 1s2, 2s1, but now its electron arrangement is 1s2 only. Beryllium's outer electron arrangement is 1s2, 2s1. Boron is 1s2, 2s2. Carbon is 1s2, 2s2, 2p1, and so on. As you're going across, electrons are starting to fill the second energy level. However, the only element whose electrons are appearing in the first energy level are lithium, and the electrons are far closer to the nucleus in the first energy level, and there is absolutely no shielding of those 2s electrons from the 3+ charge in the nucleus, and therefore the element that has the highest second ionization energy is lithium, because the electrons are being removed from the first energy level, which is much closer to the nucleus. So let's write that down again. The element that has the highest second ionization energy in period 2 is lithium, and that is because electrons will now be removed from the 1s subshell, which is closest to the nucleus, with no electron shielding.